Okay, so far we have been thinking about the different buyers' behaviors under different auction formats and been thinking about what are the equilibrium bidding strategies that we would expect to emerge under different auction formats, right? But let us now take a step back and think about the original problem of the seller, which was to kind of sell an item, right, among different buyers, right? And from the seller's perspective, we can think about which is a better auction format to sell, right? So one objective of the seller might be to maximize the expected revenue. So in that case, would the seller have been better off by using first price auction or by second price auction? Now, intuitively, the answer is not clear, right? In the second price auction, what you have is that the seller actually is explicitly committing to collecting lesser money because the seller is only charging the second highest bid and not the first highest bid, right? Whereas in the first price auction, you have the issue that the bidders on their own are reducing the bids. So that may also actually reduce what the seller can collect, right? So just to give you two examples, imagine that you have got two buyers and they are drawing their bids from 0 and 100 uniformly from 0 and 100, right? And imagine that the actual kind of like realization, which is unknown to the seller, is 90 and 30, right? Now, in this case, if the second price auction was used, then everybody is going to truthfully bid their true values, right? So the person who had valuation of 90 is going to win, but this person is only going to pay 30, right? So the seller ends up making only 30, even though there was somebody who was willing to pay 90, right? So this is what we mean by that in a second price auction, the seller, by explicitly committing to collect the second highest bid, is actually ending up probably getting less money, right? But in this case, if we had used the first price auction, then you would have got more money, right? So if we use the previous result, then the first person would have shed down the bid by half. So 90% would have bid 45, and that is what the person would have had to pay. So from first price auction perspective, if the seller had gone by that, then they would have collected more money, even though there is a shedding of the bid, right? But if you change the numbers, so for example, instead of 90 and 30, imagine that you had 90 and 60, right? So in this case, in the second price auction, the two people would have bid 90 and 60. The person who had bid 90 would have won and had to pay 60. So that would have been the seller's revenue. If we had gone by first price auction, the person who had valuation of 90 would have bid in one equilibrium, 45. And the person who had 60 would have bid 30. So you would have had actually a payment receive of 45, right? In this case, the seller would have done better if he had actually second price auction, right? If on this particular realization. Now, the question is, suppose you don't know what particular realization is going to come. You don't know if it's going to be 90-30 or 90-60 or any pair between 0 and 100. Then from a seller's perspective, are you better off under first price auction or are you better off under second price auction, right? So that's the question we want to do. So let's go back to the setup that we had. So imagine that you have got n bidders whose values are drawn independently from this uniform distribution between 0 and 1, and none of the bidders know each other's value, right? So this is the only information that is there, right? Now, if you want to calculate the expected revenue of the seller under the two different auction formats, first price auction and second price auction, what we want is the expected value of the first highest possible value and the expected value of expectation of the second highest possible value, right? So here we are going to use a result from probability theory. I'm not going to prove this result. You can try and prove it. It's not that complicated, or you can look it up on the internet as well. But let's just take it as given, this statement, right? So what is the result that we are going to use? This is saying that suppose you have got n numbers, which you are drawing independently from the uniform distribution over the interval 0, 1. And then you sort these numbers from the smallest to the largest, okay? So if you want a concrete example, suppose you are drawing three numbers from 0 to 1. Once you have drawn these three numbers, you are going to sort them from the lowest number that you have got to the next highest number to the largest number, right? So these three numbers that you have, okay? Now, the question is, what's the expected value of a number in any position, right? So you can ask the question, what's the expected value of the lowest number that you draw among these three numbers? What's the expected value of the highest number that you draw from these three numbers? Or what's the expected value of the middle one that you draw, right? So for n equal to 3, this result is telling us that the lowest value of the number that you have drawn, that is going to have an expectation of 1 divided by 3 plus 1, right? Where am I getting the 1 from? So the lowest value will be the first one on this list, right? The lowest position. So k equal to 1, and n plus 1 is going to become 3 plus 1. So that's where you get the 1 by 4, right? What's about the expected value of the highest number? So the highest number when you have got 3 draws is like n equal to k equal to 3. So then you have got, this will become 3 by 3 plus 1 or 3 by 4, right? What happens if you have n equal to 2? So then one of them is the lowest, the other is the highest. So the lowest number is going to have, again, k equal to 1 and n equal to 2, so 1 by 3, and the highest one is going to have 2 by 3, right? So that's how you can use this result, okay? Okay, where is this useful? Let's now go back to auction theory. So suppose that initially the seller was running a second price auction, right? Now, what is going to be the expected revenue? Then this is going to be basically the expectation of the second highest value. Why? Because remember, the person who has the highest value is winning, but this person is actually paying a bid which is equal to the second highest value, right? So from the seller's perspective, what the seller cares is about the expectation of the second highest value, right? Now, you've got this n numbers, right? So the second highest value in this sorted list is going to be the n minus 1th position, right? So we are going to put in k equal to n minus 1 in this expression. And so therefore, the expected value of the second highest number, which is the number in the n minus 1 position in the sorted order out of this n random values, is equal to n minus 1 divided by n plus 1, right? So this is the expected revenue of the seller from a second price auction. What happens in the first price auction? Well, in the first price auction, then what the seller cares about is the expected amount of money that the first person is going to bid, right? So what's the amount that the first person is going to bid? Remember that we had this result in first price auction, that in equilibrium, one bidding strategy that you have is going to give that the person is going to bid an amount which is given by n minus 1 divided by n plus 1 into the valuation, right? So then the expected amount of this is given by n minus 1 divided by n plus 1 multiplied by the expected value of the highest number out of this n draws that is coming up, right? So what is the highest value's expectation? So again, we go back to this result. So then the highest value is the one in the position k equal to n plus k equal to n. So then the expected value of the highest number among these n draws is given by n divided by n plus 1, right? But that's not the expected revenue, because each of the bidders is going to shade their value, right? So it's going to shade their value by a factor of n minus 1 multiplied by n, right? This is the shading factor. And so therefore, we need to multiply this with this expression to get the expected revenue. So the two n's cancel out and you end up with n minus 1 divided by n plus 1, right? So if you notice, this is the same expected revenue that we had in the second price auction case, right? And this is actually not a coincidence, right? So the significance of this is that from the seller's perspective, if you use first price auction or if you use second price auction, you end up getting the same expected revenue. And this is actually an illustration of a much more broader and much more general principle, which is known as the revenue equivalence, right? So what this result says is that a seller's expected revenue is going to be same across a very different class of auctions, and where you have like different types of distributions, not just this uniform distribution, when the bidders actually follow equilibrium strategies. Again, I don't expect you to know the result in general, because this is an advanced concept from mechanism design, but you should understand why in this case, how this revenue equivalence theorem worked, by showing that the expected revenue in these two cases end up being equal, right? So again, if you want to learn a bit more about this, you'll have to take up more advanced courses in auctions or in the area of mechanism design. So I leave that for that further course.